In this video, I'm going to go through the 3 different ways to write an electron configuration. So here's just a little bit of vocabulary to help you out. Energy levels are also known as shells. So anytime I say shell, I mean energy level, which you're aware of. Shells are then divided into subshells, which can be further divided into orbitals. We only care about the orbitals in the last notation. These are the 3 ways I'm going to go over in this video. Regular full electron configuration, noble gas or condensed, and then orbital diagrams or orbital notation. We are going to need to know how many electrons will fit on each subshell. So the subshell is represented by a letter, and you can figure out how many electrons go on them based on this chart. What you might notice is that it says max number of electrons because you have to fill them up until you get to the very end. At the very end, you don't necessarily have to have the total number. You can have any number up to this number. So for P, if it's at the very end, you could have 1, 2, 3, 4, 5, or 6. This principle right here says that you have to put an electron in the lowest energy level possible before you move on. Lowest subshell, lowest orbital. So there are 2 ways that I'm going to help you figure out what that is. So we're going to do these 2 examples, and I'll go over those 2 different ways. The first way involves this arrow diagram right here. So the arrow diagram, you need to follow the arrows. So make sure you're starting at the back of an arrow, going to the front, then the back of the next one to the front, and so on. So you don't want to ignore the arrows and just go left to right, because what will end up happening is that after 3P, you would go to 3D, which is not correct. If you follow the arrows, you'll see that 4S comes after 3P. That's because 4S has a slightly lower energy than 3D, and the Aufbau principle tells us we have to fill up the lower energy first. So this diagram can help you with that. I'm going to go over how to use this diagram, and then I'm also going to teach you the second way that you can do that. So the way this works is that the first thing you do is look up on your periodic table, how many electrons the atom has. So for fluorine, we look it up on our periodic table, and the whole number in the box tells you how many electrons you have. So fluorine has 9. I'm just going to write myself a little reminder. Then you're going to use the arrow diagram and the little chart that tells you how many fit on it. So the first thing we hit here as we go down the arrow is 1s. S gets 2 electrons. And remember, you have to fill it up before you move on. So the way you write that is you write 1, S, and 2 as an exponent. 1 is referring to the shell or the energy level, and then S is the subshell, and 2 is the electrons. So we need to keep doing that until we get to 9. So after 1s, we follow the arrows and we get to 2s. And that 2s also has 2. Okay, the coefficient, the number in front, is just the shell number. It doesn't change how many electrons fit on the subshell. So now we keep going. After 2s, we hit 2p, and p gets 6 electrons, a total of 6. It can have that many. But here, we don't need 6, because we just need this to add up to 9. And we already have 4, 2, and 2 here. So remember I said at the very end, you don't have to have the maximum number. You just have however many you need. Here, we want this to add up to 9. So we are done. This is the electron configuration for fluorine. Now let's do calcium. Calcium has 20 electrons, and we're going to do the exact same thing. And you can see this starts to be pretty repetitive. We're going to start at 1s again, because you always start at the very beginning. So we have 1s2, 2s2, 2p, but this time we're not stopping there because we need to get all the way to 20. So this time we are going to fill up 2p. Now we need to keep going because that's only 10. So the next one we go to after 2p is 3s, and that just has 2 because that coefficient doesn't affect it. So that's 12. Then we go to 3p, which fits 6, just like all the other p's. And that's 18. And then after 3p, we go to 4s. Make sure you are following the arrows, because if you go 3p to 3d, that is not right. So 3p and then 4s. 4s holds 2, and that's exactly how many we need. And that gives us a total of 20, which is what we wanted. So now I'm going to go over another way to do this same exact thing. So I'm going to do fluorine, because we've already done it. Fluorine is right here. So what you can do, instead of using the arrow diagram, is use the periodic table. The period numbers, which are over here, will tell you the shell number. The color, or the block, will tell you what subshell you have. And then the boxes tell you how many electrons are in that subshell. So if you start at the beginning, you have 1. And the first color you hit is S. And then there are 2 boxes, 1, 2. Okay, helium is colored the red color or the orange color because it is part of the S block, even though it's over here. So that means 1s2. 2s2. And then we go, there's nothing here, so we go to P. 2p, 1, 2, 3, 4, 5. And you do count the element itself. And so that's fluorine. And that's the same exact answer we got before. There are a couple tricks to this little method. For the D block, subtract 1 from the period number. And for the F block, subtract 2. So let's do germanium so I can show you what that looks like. So for this one, we would start at the very beginning, always start at the beginning. So it would be 1s2, then we're here, that's 2s2, 2p6, 3s2. So after we go through 2p6, we go here to 3s2, then 3p6, and then after 3p6, we go to 4s2. We have to keep going, we're not done yet. So when you hit the D block, the period number, which is these numbers over here, also our shell numbers, you subtract 1. So instead of being 4D, this one is 3D. Okay? And then you do the same thing, you count the boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's going to be 3D10. But then when you get to P, you're not subtracting that 1 anymore. So this goes back to 4. So now it will be 4P2. And that's why some people prefer the arrow diagram as opposed to the periodic table method. I do think it's very helpful for you to have at least an understanding of both, because this is a good check, and it also helps you because you can figure out where it is supposed to end, meaning where your configuration is supposed to end. So even if you use the arrow diagram, you want to make sure, if you were doing germanium, that it ends in 4p2. Okay, so it's a good little check at the end. But please remember about the D block. And then for the F block, which is down here, this is 4F and this is 5F. And they go right in here, actually. All right, so that's both methods of writing your electron configuration. We're now going to talk about some other ways of writing it, of expressing it. So the first one is noble gas notation, also known as the condensed version. And there are, again, 2 ways to do this. The long way is to write out your regular electron configuration. So for sodium, we need 11, and then after you've done that, go back to your periodic table and you look backwards until you hit a noble gas. So remember, the noble gases are in this column right here, 8A or 18. And if we're at sodium, that's right here. So we know that's not a noble gas. But that's number 11, atomic number 11. If we go to atomic number 10, that is a noble gas, that's neon. So that's the noble gas we're going to pick for this configuration. What you do then is you go back to your configuration and you bracket the 10 total electrons. So here we have 2, 4, 10. You then replace those electrons with the symbol for the noble gas. And copy the extra on the outside. So that's your condensed version. You might have also noticed that if you understand the periodic table way, there's an easier way to do this just by using your periodic table, figuring it out from there and counting from there. So for nitrogen, for example, you want to count backwards until you hit a noble gas. So don't go to neon even though it's closer, because that's too many electrons. You won't be able to bracket the correct number. So if you go backwards and you get to helium, that's going to be your noble gas. So if you want to do kind of a quicker way, you can write helium and then after that, you can just do it from there. So you do 2s2, 2p3. So you can do noble gas notation either way. The last thing we're going to talk about is orbital notation, which sometimes is referred to as an orbital diagram. So there are several different ways to do this, different ways you'll see it. The first thing you're going to do for all of these is write the standard form electron configuration. So just the first one we learned. Then you can write either boxes or lines or circles. So I'm going to do two for you. The first one I'm going to do is phosphorus. So this chart right here tells you how many orbitals you get. So your orbitals are going to be your lines. Your electrons will be your arrows. And the lines can also be boxes. You'll see that a lot. So here, you write one line for each S, 3 lines for each P. And then however many electrons are in that subshell, you draw arrows for that. And you can draw either full arrows or half arrows. You do need to have one pointing up and one pointing down. And that's to show something that's called the Pauli exclusion principle. And that means that we need to have opposite spins if electrons are on the same orbital. So to show that in our diagram, we put one pointing up and one pointing down. There's also something called Hund's rule. Hund's rule says you need to put one electron on each orbital if they're in the same subshell. Once there's one on each one, then you can start doubling up. So you'll see that doesn't make a difference if the subshell is full, like 2p6 doesn't make a difference. But when we get to 3p3, it absolutely does make a difference. If you didn't know that rule, you might do this. And that is not right. The reason why that's important is because this unpaired electron tells us where the element can bond. So phosphorus can bond in 3 places. But if we do it the other way, and we just have one unpaired electron, that means it can only form one bond. And that's not true what we see in the science world, in the natural world. So this diagram is trying to explain what's going on in the natural world. So if you don't do it correctly, you might think that there's different things happening. So now I'm going to do carbon. Same thing. I'll do the boxes this time so you can see a little bit of a difference. And you're going to put the arrows in the box this time. So I did carbon to show you that even if you have an empty orbital, you still have to draw it. So what I usually tell my students is draw all the orbitals first, meaning all the boxes or all the lines. Because you don't want to get rid of this just because it's empty. You need to show that you understand that there's an empty orbital here. Okay, that if P does get 3 orbitals. So, of course, make sure you have one in each one and they're not doubled up because they don't have to be. And then leave that empty one there. And that's it for electron configurations for this intro video.